Hi guys, this is A2 Chemistry, Analytical Chemistry, and we are looking at combined technique. Question 4. This question is about compound TCXHYOZ. Part of the mass spectrum of T is shown. The peak heights of M and M plus 1 peaks are 33.9 and 30 and 3.4 respectively. So as we can see by the ME values on the x-axis, the MR of this compound is 150. And calculate X, the number of carbon atoms present in T. So the formula for calculating X is N equals 100 upon 1.1 multiplied by height of the M plus 1 peak divided by the height of the M peak. This will be equal to 100 upon 1.1 multiplied by 3.4 upon 33.9, which gives us a value of 9.1, which will be rounded down to 9 carbon atoms because the number of carbon atoms is always in whole numbers. So the value of X is 9. Deduce the molecular formula of T. So we have an MR value of 150 and we've got 9 carbon atoms. So 9 into 12 is 108. If we subtract 108 from 150, we are left with 42 as the remaining mass. So out of 42, if we subtract one oxygen atom minus 16, we are left with 26. 26. So we removed one oxygen atom, and from 26 we will remove another oxygen atom. We are left with 10. We cannot remove another oxygen atom, so the 10 has to be hydrogen, which means in total we removed two oxygen atoms. So the molecular formula of this compound has to be C9H10O2. The mass spectrum has a peak at ME 119. Identify the fragment lost from T to produce this peak. So the MR of the compound is 150. The remaining fragment is 119. So the fragment lost has a mass of 31. So if we have one carbon, which has a mass of 12, and we have one oxygen, which has a mass of 16, so together they have a mass of 28. And 28 separated from 31 leaves 3 hydrogen atoms. So the compound or the fragment that was lost was CH3O positive. So this is the fragment lost from T to produce a peak at 119 mass to charge ratio. The infrared spectrum of T is shown and they've labeled two peaks V and W. So W is around 1300, so this should be C single bond O, and V is around 1700, a little over 1700, so this should be C double bond O. Identify the type of bond responsible for each of the peaks V and W. Use the data book to help you. V is C double bond O, W is C single bond O as identified already. The proton NMR spectrum of T and CdCl3 is shown. So in total, we've got 4, 5, 6, 7, 8, and 10 hydrogen atoms in 3 different environments. And remembering peaks, the peak with 4H written on it belongs to a benzene ring with 2 substitutions on it because it has only 4 hydrogen present. Then we've got 3 hydrogens in 2 different environments. One is next to C double bond O, CH3 next to C double bond O because of its chemical shift value range of a little above 2 and below 3. And the other one is a CH3 next to an oxygen atom because of its chemical shift value being close to 4. So we have identified the three different environments which have peaks in the NMR spectrum of T. So it asks complete the table for the proton NMR spectrum of T. Use the data booklet to help you. So the peak at 3.9 belongs to an alkyl group next to oxygen, and alkyl group having three hydrogen atoms. So CH3 next to oxygen, and that between 7.2 and 7.9 belongs to the aromatic ring. And this aromatic ring has four hydrogen atoms present with two substitutions. The peak at 2.4 ppm is due to a proton attached to a saturated carbon atom. The peak at 2.4 is due to a proton attached to a saturated carbon atom. Okay. State two possible types of protons. So one of the protons is the one that we identified, which is CH3 next to C double bond O, and another one that we did not identify while identifying the peaks is CH3 next to C6H4 in this case, because the peak for C double bond O is in the range of 2.2 to 3.0, while the peak with the alkyl group next to the aromatic ring is 2.3 to 3.0. The two peaks are very close to each other, which means that this group is similar to the CH3 being next to the aryl group or the aromatic ring. So what makes more sense is that CH3 is next to the aromatic ring and not next to C double bond O, because in total there are nine nine carbon atoms present. So six of them belong to the benzene ring, one of them belongs to the CH3 single bond O, and one of them would belong to another CH3, which may or may not have a C double bond O present next to it, because there are two oxygen atoms present. So it may have an oxygen atom as well. So we'll have to find out what is the structure of this compound. So both of these are possible as far as the first peak is concerned. The first peak with 3H written on it, which is a singlet. Adding D2O to T does not change its proton NMR spectrum. What does this tell you about the functional groups present in T? Well, it tells us that the functional groups present do not contain any labile protons. Labile protons are protons that undergo proton exchange. So there is no proton exchange taking place on addition of D2O, so no labile protons present. Use the information to draw two possible structures of T which are functional group isomers of each other. Like already identified in the NMR spectrum, we can have the CH3 group next to a C double bond O group, or the CH3 group next to the aromatic ring. So in both these cases, we will have two different functional isomers of the same compound. So one thing is for sure, both of them will have a benzene ring, and the benzene ring will have two substituted groups present on it. So in the first case, let's place a CH3 group next to the aromatic ring, which leaves us with a carbon atom with a double bond O, a single bond O, and CH3 present next to it, because we have a peak for a CH3 next to oxygen. So in order to complete the molecular formula, there is one carbon and one oxygen remaining. So that would be placed here, and this would form an aromatic ester. In the other molecule, if we place the oxygen next to CH3 attached to the benzene ring, this becomes an ether, which leaves us with a C double bond O and a single bond CH3 present, which is also possible according to the first peak in the NMR spectrum given. and this also completes the formula of the given compound, the molecular formula of the given compound. And the C double bond O group here belongs to a ketone. So these are the two structural isomers which are functional isomers of each other that satisfies the NMR spectrum given in this question. Question 5. Serotonin is converted by enzymes in the liver to compound M. By reference to the data booklet, suggest how the infrared spectrum of M would differ from that of serotonin. So M would have a peak for the C double bond O group in the range of 1640 to 1750, which would not be there in serotonin. It would also have a peak for the OH group attached to the carboxyl group, which would be in the range of 2500 to 3000 wave numbers, which would not be there in serotonin. And serotonin would have an NH2 peak in the range of 3300 to 3500, which would not be there in M. Rest of the molecule is the same for serotonin as well as compound M. So only one of these needs to be quoted. So we can quote any one of them. All three are equally likely. So let's quote the one for the NH2. So we will write serotonin would contain a peak in the range of 3300 to 3500 wave numbers, which would be absent in M. Similarly, we can write M contains a peak in the range 2500 to 3000 wave numbers corresponding to the OH of the COOH group, which would be absent in serotonin. Or we could write M contains a peak in the range of 1640 to 1750 wave numbers corresponding to a C double bond O group, which would not be present in serotonin. The proton NMR spectrum of M dissolved in CdCl3 shows 8 peaks due to the 8 different types of protons present in the molecule. The proton NMR spectrum of M dissolved in D2O was recorded. Predict the number of peaks that would be seen in the proton NMR spectrum of M in D2O. So the peak due to the OH attached to the benzene ring or the phenol group, and the peak due to the COOH group would disappear. So if two peaks disappear, we are left with 6 peaks. The number of peaks would be 6 peaks. And the NH group present may also undergo proton exchange. So if the NH also undergoes proton exchange, we could end up with 5 peaks. So if the NH does not undergo proton exchange, we have 6 peaks. If the NH undergoes proton exchange, we have 5 peaks remaining in the NMR spectrum in the presence of D2O. So explanation, the OH and NH groups contain labile protons which undergo proton exchange. And we can also accompany this with an equation. The equation would be ROH plus D2O giving us ROD and HOD, or we could have RCOOH plus D2O giving us RCOOD plus HOD, or we could have R NH plus D2O, giving us R2 and D plus HOD. Any one of these three equations is equally suitable as an example to show proton exchange, and it can be given as an example along with the text written. Question 6. Cumin is a spice used to flavor food. Two compounds responsible for its flavor are cuminaldehyde and cuminyl alcohol. Structures are given. Deduce the number of peaks that would be present in the C30 NMR spectrum of cuminyl alcohol. So if it is C13, then we would have a peak for this carbon, 1. We would have a peak for this carbon, 2. We would have a peak for these two carbon atoms, 3. We would have a peak for these two carbon atoms, 4. We would have a peak for this carbon atom, 5. We would have a peak for this carbon atom, 6. And we would have a peak for these carbon atoms, 7. So altogether, the number of peaks are 1, 2, 3, 4, 5, 6, and 7. So in total, we have got 7 peaks for the carbon 13 NMR spectrum of cuminyl alcohol. Identify two bonds that are responsible for the differences in the infrared spectra of cuminaldehyde and cuminyl alcohol and state their absorption ranges. So, in cuminaldehyde, we've got a C double bond O group present. The C double bond O group present would give a range in the carbonyl region, which would be 1670 to 1740. So that would be 1670 to 1740 wave numbers. And we would have a peak for cuminyl alcohol with the OH group or the CO group. So for C single bond O, the range would be 1000 to 1260 wave numbers, and for the alcohol OH group, the range would be 3200 to 3600 wave numbers. So what they have asked is to give the values for the bonds. The bond responsible for the difference. If we write for cuminaldehyde, it is the C double bond O group, and the range is 1670 to 1740 according to the infrared absorption data sheet. And in cuminyl alcohol, we've got the OH group for the alcohol, which gives us a peak, a broad peak in the range of 3200 to 3600 wave numbers. This one can also be replaced by C single bond O. Two molecules of compound F react together under suitable conditions to form compound G. Some information about compounds F and G is given. The mass spectrum of F has a peak due to the molecular ion at 106 and a peak at Me 107 with an abundance of 8% of the 106 peak. The mass spectrum of G has a peak due to the molecular ion at 212 and major peaks at Me 91 and 105. Both F and G contain oxygen and are neutral compounds which are insoluble in water. The H1 NMR spectrum of F includes a singlet peak at 10 due to 1 proton. The H1 NMR spectrum of G includes a singlet peak at 5.1 due to 2 proton. When G is heated with dilute sulfuric acid, benzoic acid and phenyl methanol are produced. Use the information to answer 1 to 6. Okay, so the last point, benzoic acid is this, and Phenyl methanol. Phenyl methanol is this CH2 with a benzene ring and OH here, and for this it would be C double bond O single bond OH. So if we add these two together to form the ester that underwent hydrolysis, we end up with this compound C double bond O single bond O CH2 and then the benzene ring. So we have actually identified compound G, and it says that two molecules of compound F react together under suitable condition to form compound G. Okay. So explain how the mass spectrum of F shows that a molecule of F contains 7 carbon atoms. Show your working. So in order to show the working, we have the formula of N equals 100 upon 1.1 into percentage of M plus 1 upon percentage of M. So if it is a total of 8% of M, so M would be 100% then. So this would be 100 upon 1.1 into 8 upon 100. So 100 gets cancelled. This becomes 8 upon 1.1. And 8 upon 1.1 gives us a value of 7.3, which needs to be rounded down to 7 since carbon atoms are in whole numbers. So hence we have proved that 7 carbon atoms are present in a molecule of F. Suggest the molecular formula of the fragment of G at Me91. So Me of 91. So this would be a benzene ring. A benzene ring has C6H6, so 6 12s are 72. 72 plus 5, which should make it 77. So 77 plus 10, 87, 88, 89, 90, 91. We have got 14 left. So one carbon makes it 12 and one hydrogen makes it 13. So C6H and two hydrogen makes it 14. So we have C7 and H7. So 7 12s are 84. 84 plus 7 is 91. So the molecular formula for the fragment of G at Me91 is C7H7 with a positive charge on it. Suggest the molecular formula of F and G. So the molecular formula of G would be C14 as drawn above, and then we have 1 2 3 4 5 6 7 8 9 10 11 and 1 12 hydrogen atoms, and we have got 2 oxygen atoms. So that would be the molecular formula of compound G. And as for the molecular formula of compound F, we would have C7, H would be 6, and 1 oxygen atom would be present. Because if we look at this structure here, we have got C6, actually C7, C7, H567, H8, H would be 8 and 1 oxygen. So this should be compound F. So C7, H8 and O. So now we have identified the molecular formulae of F and G. Just to revisit structure F, the question said that two molecules of compound F react together under suitable conditions. So two molecules of the alcohol will not react together under suitable conditions. It means that F is not the molecule that was marked in red. In fact, the two molecules that reacted together, the benzoic acid and phenyl methanol, are both made from compound F. So we have a CH2OH group that is made from F, and we have got a COOH group made from F. A COOH group is made by oxidation, and an alcohol group is made by reduction. That means F has to be an aldehyde, because oxidation of an aldehyde leads to the production of a carboxylic acid, and reduction of the aldehyde leads to the formation of the primary alcohol when CHO becomes CH2OH. So this is F. So reconstructing the formula for F, it is not C7H8O, it would be C7H6 and O, because compound F is benzaldehyde. Suggest the structures for compounds F and G. So we had just figured out that the structure of compound F is benzaldehyde. So let's make the benzaldehyde. And we had already identified the structure for compound G, which was made from benzoic acid and phenyl methanol. So that would be, the benzoic acid portion would be this C double bond O, and the phenyl methanol portion would be this CH2 and then another benzene ring. So this is the structure for compound G. On the structures you have drawn in 4, circle the proton responsible for the H1 NMR peaks at 10 in F and 5.1 in G. So the one for 10 in F would be the protons that are part of the CHO group, because the peak for the aldehyde lies in the range of 9.3 to 10.5. So 10 lies in that region. And the peak for the 5.1 chemical shift value is because of the CH2 group present between an aromatic ring and next to an oxygen atom. So this would give us a peak in the range of 5.1 in compound G. State state the type of reaction that G undergoes when heated with dilute sulfuric acid. It undergoes acid hydrolysis, because H2SO4 is an acid, and when an ester is hydrolyzed, it results in the formation of an alcohol and a carboxylic acid. So acid hydrolysis occurs when G is heated with dilute sulfuric acid.